So hello everyone and welcome to our second day, session 2 on Astronomers Toolkit. Now today's session will essentially be a hands-on session where I'd be actually showing you how to do the stuff I was talking about yesterday. And hence today I hope that all of you all have your laptops with you and we can start working with our laptops, right? So first of all, yesterday I had a little chance to talk to you about the Astrophysics Data System. The Astrophysics Data System is a system which basically has material which we can use to access astronomy data. So what you saw me do was you can just put it on your Google. On Google, you can search and say Astrophysics Data System. And the first hit itself will be NASA ADS, right? So please click on that. Now, the NASA ADS is a system through which you can directly access all literature available on a certain object, on any object. So what we are going to do is, let us, for example, try to study, today what we are going to work on is trying to study a star cluster. We'll take up some young star cluster, for example, 2264 or 1893. And what we are going to do is we are going to use Gaia data to basically get parameters to study the star cluster, right? Now, like I mentioned to you, a star cluster is a system of stars which was born from the same molecular cloud, and hence they have the same age and the same distance from us, the same chemical composition. Only the stars differ in their masses. And therefore, what I'm going to show you is we're going to look about how can we actually, so let us, for example, take up the cluster 1893. So please click on your Astrophysics Data System and we can load in over here. And I'm clicking on this for the basic HTML, right? So like I mentioned, this is a database where you will actually get, so supposing you decide to start work with a cluster. Let's say, for example, you decide to work on NGC 1893. So first thing we would do is we can actually look for what are the papers which are there on this object, right? So for example, I can write NGC 1893, right? If I want, I can actually put it even in the title, abstract and title. I can put it as part of this. So I'll paste this and I will get this over here. So so you can just add the keywords. I don't know who has published data on this cluster. So I just write NGC 1893.
Prisha? I think we lost you.
Let me remove 1893. I'll just put 1893. And here you can see is that you can see these are the set of papers which were published on this cluster. So for example, here there is a deep VNI CCD photometry of this thing, which is available from this. So for example, if I look at this paper, I can click on this paper. I will click on it and it's going to give me details about this paper, right? So I can click on this. I don't know why the net seems to be a little slow.
I'm sorry, Priya.
Yeah. You can see my
I think
fine.
Yes, we're looking it very good, but with small cuts in your internet connection. So I will suggest you to cut off your camera. Maybe that will work better.
Yeah, that's a good idea. I'll do that. It'll be better for me too. Right.
Thank you.
So is it getting any? I've put off the camera. Is this a little better? It should be better.
Yeah, I think so. So far, so good.
Yeah. Okay. Thanks a lot. Yeah, do let me know when there's anything. So for example, here you can see that these are the set of papers which are there on this cluster, right? So for example, I can even look at this paper. You can click on this. And here you can see it's giving me details about a paper which was published on this thing. What happened? I don't know. Okay. I'm sorry. There seems to be some problem. So I'll go back to the same thing. I'm going to look at this. I don't know why. There seems to be some problem with ADS. So what happens is, with this source, I can actually look for material on this cluster. Let me try to see this one. I don't know why ADS is doing this to me today. It should not be doing this, but it's doing this. Let us go ahead. No problem. I will continue with other things. So let us, so what happens with this is you can actually see what are the papers that people published on this cluster, for example. Here you can see there's a grid which actually shows you the increase in number of papers on this cluster. These are the refereed journals, the non-refereed journals. You can actually search by author-wise if you wanted to search for author-wise. And this link will also give you things about, you see over here, there's a catalog. So for example, somebody observed this thing and has the LS, this is the local standard of rest velocities. And you can click on this, and with this, you can actually access the catalog, right? So for example, if you click this, I don't know what's wrong with this today. Why is this happening? But you can get details about this. So let's say, for example, if you started working on 1893 and you got information about it, you collect information about this cluster. Now, the next thing you can do is, for example, I showed you Aladin yesterday, right? Please open your Aladin if you have it. And once you open it, you can put the name of this cluster. I am putting the name over here. I can write NGC. Sorry, oh, I typed it twice. I'm going to write NGC 1893. And if you see over here, this is a visualization tool, right? So what this basically does is it's going to show you an image of this object. And this image you can see is, this is an image of this cluster called 1893. And you can see it's marked over here, but this is from the WISE catalog, right? You can look over here on the top, it's written all WISE color. Now, WISE is a satellite which actually observed the sky. It has an all sky catalog, and it looks something like this. Now, what we're going to do is, yesterday I showed you all how to, install TopCat. I hope all of you all have installed TopCat. You will have the icon for TopCat looks like something like this. This is the cartoon character TopCat. So you will click on this, and you can actually open something like this, right? So there are some earlier plots over here. Please ignore them. And here, this is your TopCat screen. Now, with TopCat itself, we can access Gaia data. Okay. So I will show you how to access Gaia data directly using TopCat. So over here, up over here, you can see there's a button which says VO, which basically stands for Virtual Observatory, right? Another very important thing which you can notice in the screen over here is you can see clients written over here. And here, this is what is called the SAM connector. So this basically connects all the virtual observatory clients. So for example, TopCat is connected to, this is the SAO DS9, which I showed you yesterday, which is a visualization tool. Then this is Aladin, which I just showed it to you. And here there's DS9, which has come up twice because I think it's open twice over here. So what we're going to do is please click on VO, where you have VO over here, and click on cone search. So what we're going to do is we are going to access the Gaia data for NGC 1893. So click on this over here, and here at the keywords, right? Sorry, I had used this earlier, so that's why you can see it. I will run it again. Please type Gaia EDR3. EDR3 means the early data release 3 of Gaia data, right? And then you'll click on Find Services. So please write keywords Gaia EDR3, and you'll say Find Services. So this is telling you all the services where we can find Gaia data, for Gaia EDR3 data. Like I told you yesterday, data lies in data centers. And there are many data centers on which data is available. So you can see over here, there is an RE, this is at Heidelberg, which is there. There is at ESA, also the data center. There is also data sitting at other locations. This is from Vizier, which we spoke a little bit about. And these are other sources. So you can click on any of them. You can even take this one, or let's take this one, the one at ESA, right? And once you take ESA, you can here specify NGC 1893, right? I don't know the coordinates of this. I just know the name of the object. So I just write 1893. and I say resolve. What Virtual Observatory does is once you give the name, if you remember yesterday I showed you Simbad, which is part of the CDS Strasbourg. So if you say resolve, it will resolve and it will tell you the coordinates. It's telling you now the coordinates of this cluster 1893. So it tells you the array of this cluster is 80.727 and the declination is 33 0.444. So therefore, this is the array and dec of this thing. Now I'm going to download data of this star cluster within a certain radius. So let me say I download the data within 20 arc minutes, right? So you have to edit, and over here, you change this unit to arc minutes and make this radius as 20 arc minutes. So what we are basically trying to do now is we are trying to download the Gaia EDR3 data for NGC 1893 within a radius of 20 arc minutes. Now you're going to plot, you'll say okay. And now here what you're seeing is that we are directly downloading the Gaia EDR3 data for NGC 1893 that you can see over here. So I hope all of you all are going with me. If there's anybody who has any doubts, you can please ask on the chat, or you can ask me just now. I hope people have managed to do this, right? So I hope all of you all have managed to open TopCat and query the Virtual Observatory for 1893. Please let me know if anybody has a problem, right? I'm just going to pause just now while this data is downloading, but please let me know if everybody has managed to do this. Right? Is everybody managing to do this? Yeah, okay. Yeah, okay, thank you. Thank you, Louis. Thank you for your answer. I'm happy to know that you are with me. Very good. So I'm just waiting for this data to download. It's not yet downloaded. So I'm just waiting. If the others have managed to download the data, you can this thing. Meanwhile, we'll go back to Aladin and we'll have a look at Aladin, and let us look at this. So now Aladin is letting me visualize images. So for example, this is 1893 in Allwise. I can also observe 1893, for example, in DSS. DSS is the digital sky image. And you can see that that's coming over here. So I'm going to delete this one. Yeah. So you can see over here, this is the DSS image. What Aladin does is here, this is the same thing being looked in different wavebands. So this is the DSS image, which is optical wavelengths, and exactly overlaid on this is the WISE image, which is in the mid-infrared, right? So you can put it like this. On this, I can further overlay if I want to, for example, look at this using, for example, Gaia. I can also do it with Gaia. But Gaia does not give me images. I can also observe this with TOMAS. TOMAS observes the sky in the near infrared, and you can see that this is the near infrared image of NGC 1893. Again, this is just overlaid on the other image, right? So this is the TOMAS image. This one is the WISE image, and this one is the optical image, right? So you can see that TOMAS, because it's a near infrared, it actually looks through this thing. Now, the red squares that you can see coming up are basically coming up from the Gaia catalog, right? So you can see over here that, let me just switch it off for a minute. You can see we had already started querying the Gaia catalog for this object. So if we look at it in WISE, let me center it here. It's around the center. And now since I've clicked on Gaia, you can see that the stars, the Gaia stars, are being plotted onto this. There's too much of red over here, so let me just, I will make it another color just to make it a little more convenient. Let us make it this color. So what I did was I right-clicked on this. I clicked on properties and I changed the color. So now you can see over here, I can see all the Gaia sources within this area, right? And if I want to see details of it, all that I have to do is use my mouse, mark these parts, and here in this drop down, you can see this is where the Gaia data is being listed. So for example, you can see there is the RA, there's the deck, the source ID, the RA error, deck error, and Gaia measures what is called the parallax, right? So the parallax, this is in milliarc seconds, and therefore if I want to get the distance, which is 1 upon parallax, it will be 1000 upon parallax, right? So 1000 upon parallax will give me the distance. This is the error in parallax. This thing also gives me the proper motion, which is PM, the proper motion, which is the motion of the star in the plane of sky. And these are the two components of the proper motion. Here you have the proper motion in RA, and here you have the proper motion in deck. This is the proper motion in RA error, proper motion in deck error. So this is giving me all these details about these stars. It also gives me various other parameters. For example, Gaia gives me the photometry. It gives me, this is the photometry in G band, the mean magnitude in G band. And here, if I go further, I can even get the color. So the color is given to me by BP minus RP. Here. And in that way, I can get all the parameters. So if I want to look at a particular star, I can just click it over here and it gets highlighted in this image over here, right? I can highlight whatever I want and I can put it like this. Now the table which I've got over here, it works both ways. I can use that to actually, let me do this once again. I don't know why this didn't do it. It should do it very fast, right? Now what happens is Aladin can talk to TopCat as well as TopCat can talk to Aladin. So for example, if I've marked these things, I can even send them via the SAMP server straight to TopCat, or I can use it from here and get it with this, right? So either way, I can get the data of 1893 using this method, right? I don't know why there seems to be a little bit of a problem with my internet, and hence I can't, but this is, you can see, this is the SAMP server. So if I click on this, I click on SAMP, and I can say, I can select a plane, I can select this plane. This is my plane. I can do this, and I can say broadcast, select, I can say this, and I can say apply, and I can send it to wherever I want to send it. Similarly, over here also, I can open this thing. I don't know why I seem to be having a problem over here in downloading the data. This is strange. This is very strange, but I can find a way around it. The other way around it is you can look over here. Let's get back to our, to our browser. I can also access data using what is called the, right? The VIZER. This is called Vizier. Vizier is also hosted at CDS,
Risha, are you there? I think we lost her. Is it me or nobody's hearing her? No.
I seem to have exited the meeting from the other side. Yeah. Can you hear me from here? Hello?
Yes.
Can you hear me over here?
Yes, now we can. but we are not looking at your presentation.
Yeah. Okay. Okay. I'll just now do it again, and let me just do it. I will. Yeah. Okay. So I'm going to open another browser and show that to you. I don't know why I seem to be having some problems with the net.
Yes. I think that because it is Friday, we had a lot of problems today.
Yeah, I don't know why. But okay. So now can you see my screen?
Not yet, no.
You can see a browser?
No, you're not sharing your screen.
Okay, 1 second. I'll just do it again. I don't know why there is this problem today. Okay. Yeah. Yeah, so now can you see my shared screen? Yeah. Okay.
Yes.
Yes. So yeah. Okay, so now you can see my browser?
Yes, now it is okay.
Okay, very good. Okay. So and I will go back to TopCat. Let me open TopCat again. So here I'll just repeat that thing because I'm using another system. I'm using another computer, so I'll just use it over there. Okay. So we clicked on VO. I clicked on cone search, right? Over here I said Gaia EDR3. We say find services. I'm just repeating the steps that I did, right? Now here I choose Gaia at ESA. I write my name of my object, NGC 1893, right? I resolve it. I get the thing. And now here I look for data within 20 arc minutes, right? So I take within 20 arc minutes and I say 1 minute. There's an OK button. I need to press that OK button. So please press the OK button, which is sitting down. 1 minute. I'll just pull this and get it fine. This is okay. So now what happened is I am downloading this data and hopefully it's doing it well now because the other time it was not doing that. So like I mentioned to you all, Gaia is an ESA satellite which observes the whole Milky Way in a very good way. It basically gives us parameters like very accurate RA, right ascension declination of stars. It gives us the parallax of stars. That means the distance. So the distance is basically 1 upon parallax. It gives us the proper motion of stars in both coordinates, which is in the RA as well as in the DEC, right? And then the big thing is that this is very helpful typically when we want to find out the membership of a cluster. Supposing we are looking for a star cluster, what we are going to do now is we are going to actually find out the distance, find out the members to a cluster and hence also find out the distance to that cluster, right? And that's what we are going to do now with our thing, right? So I'm just waiting for this data to be downloaded and I hope you all are also downloading this data. You see that there are a large number of sources which are coming out from this because we've taken a 20 arc minute radius. Probably I should have taken something smaller. It's too big and there's lots coming up from there. So we will do that. And here you can see this is my data, right? This is the data. Like I told you, the stars have a right ascension, a declination, parallax error, proper motion in RA, proper motion in DEC, as well as photometric data, which includes the G-band magnitude. You can see the G-band magnitude here, as well as the color, which is the BP minus RP, right? Now, if I were to look at this cluster, you can click on this. This is giving you a plane plotting window. And in the plane plotting window, if we plot it, we can mark the RA and the DEC, right? And this is the data that we have downloaded. But the problem is that there are so many stars and we do not know which of these stars are members of the cluster, right? But like I told you that the cluster stars are number one at the same distance, and number two, they will obviously have the same velocities because all these stars are moving together. They were born from the same cloud, and hence they will have the same amount of velocities, right? And therefore, we are going to use this very important piece of information for our work. So what we're going to do is I can, number one, plot these stars. This is the same plot which I'm using. Please use the same plane plot window. And instead of RA and DEC, here we are now going to plot PM RA, right, versus PM DEC. So this is basically the proper motion in RA and the proper motion in DEC, right? We are going to basically study that. And you can see that this is what the plot looks like. If I want to see a zoomed in version of it, one way is you use your mouse and you can zoom it nicely, right? The other way what TopCat lets you do is TopCat actually lets you adjust your axis. So I'm going to show you both methods. One is this, right? And so what happens is if you have a set of random stars, right, they will have motions in all directions, right? And therefore, you will have a clustering of them around the point 0, 0, which you can see over here. This is approximately the point 0, 0. You can see that there's a little bit of clustering around over here. And that is just because of the random motion of stars. But if we want to now look for these stars in terms of this clustering is nothing, but I hope you can see that there's a clustering happening over here, right? This is a darker piece over here. Now this one has a center somewhere over here. You can look down, it's written minus 0.34 versus with minus 1.4. So these are the stars which actually make up this cluster. So what we're going to do is we are going to say click on subsets, say draw blob subset, and we mark this. I say over here subset, finish drawing mark, and I can call this C, where C stands for cluster, right? And this is this thing, and I can say add subset. So these are these stars which seem to be having a clear motion together. I will show it to you once again. Look over here. If I plotted, what I did was I plotted proper motion RA with versus proper motion DEC. You can see that there's a clumping of stars at this point over here. So I marked these and I called that using, I clicked on subsets, draw blob subset. I did that, and with that I got my C, which is this, right? So the first cutoff we have made is the cutoff which we have in terms of velocities. The other thing is that we know that these stars are going to be approximately at the same distance. So I can click on histogram. Okay, I'll click on histogram. And like I told you, the distance is approximately 1000 divided by the parallax. Why? Because the parallax which we have over here is basically in milli arc seconds, which is 10 power minus 3. So therefore, if I do 1 upon parallax, it will basically give me 1000 divided by parallax. So here in the drop down menu, I will click and I will select parallax, and here I'm going to write 1000 divided by parallax. So here this is my spread of parallax, right? I can adjust this better because there are these points over here. So let me instead, these are in distances. So I'm going to adjust the range, right? I can say let my minimum of X be 0 and let the maximum supposing be 5000, right? And you can see that this is how the range comes in. I can even adjust the range for, this is for X. For Y, I can just adjust it by even just dragging this. So I drag this and I can make this like this, right? So this is telling me the distribution which I have in terms of distances, right? But we have already pre-selected our stars, right? In such a way that I already have my, I'm sorry with this thing happening like this, but I'm going to mark my subset, right? I have a subset and that subset is what I will mark here. So if I put my position, let me do this. I'll do this here. I can do this again, the same thing. And I'm going to put this thing with 1000 divided by parallax, right? And you can see that we have subsets. One subset is all and one subset is C. So this was the set of stars which seem to be moving with the same velocity. So now I will not consider all the stars. Let me remove these all stars and let me concentrate on this, right? This is my the thing which I am worried about, which is my cluster stars, which are over here. And what I'm going to do is I'm going to adjust again the range in which I can see these stars in a better way, right? So I will instead change my range from 0 to, say, for example, 200, right? I'm going to change this like this, and I will adjust this. So you can see that for these stars which were co-moving, I do have something of this, and these are the stars which are co-moving. I can actually click on the, over here in this plot, I can actually click on forms. So let me go back to position. We need to actually see this position plot. I'm sorry that because I had to change my system, there's a little bit of a problem over here, right? And you can approximately, you can actually fit this to a Gaussian. If you fit this to a Gaussian, you can actually get the value which is there for this, right? So I will actually move this a little bit, right? I can move this a little bit, and I can move this also a little bit, so that I could see my, I would like to see my thing better, right? So let me go over here, and this is my, we are concentrating on this, which has C, right? I can click on form. If you click on form, you'll see forms, and here you can add a Gaussian, right? So let me add the Gaussian over here. You can see there's an Gaussian I've added over here, which we can't see. I don't know why can't we see the Gaussian, but you can see the values of the Gaussian fit, which is coming over here. Ideally, it should have shown you a Gaussian. It's not sure. Oh, it's doing it for all. That's why the problem is, because it's doing it for all. I'll have to tell it to do it for this. So my form Gaussian is for this. Right. So I'm going to plot my histogram over here. And let us say, for example, if we say that this mean value, we can even do it like this. If you come over here, you can see this is the stats. So if I click on the stats over here, I can see that for all, I have a total distribution. But if I just go for C, then I can see that for C, my mean parallax is 0.240, right? So if my mean parallax is 0.240, I can use that to get the distance to NGC 1893. So I can actually plot it, and I can do it over here, where, right? So what I'm going to do is, I have 0.24, so I can take 1000 divided by 0.24, and that is the distance to this cluster in parsecs. So you can see it's 4166. That means the distance to NGC 1893 is 4166 parsecs. It's approximately 4 kpc away from us, right? So now we have actually managed to find out the distance to 1893. And we also know the stars, which are members. Now we can plot this on Aladin. So I'm opening Aladin now. I've clicked on Aladin Excel. And so here's Aladin. Okay. I think I've doubly clicked it. So that's why I've ended up with more than one Aladins. I'm just going to have one. Okay. So now here I have my object, which is NGC 1893. Let me, for example, plot it with Y's. So here is the Y's data for NGC 1893. Now what I'm going to do is I can actually use this. I can say row subset C with TopCat, right? And this should have ideally, let me sap this onto Aladin, right? But before that, I'll do another thing, which I will do this. And okay, so let me start this. So now what I'm going to do is I'm going to show you a very beautiful plot where you can actually get convinced that these are actually cluster members. So for example, here you can see I have plotted the cluster, right? I have plotted the cluster 1893. And if you see is these are only the cluster. If I was to plot all the stars, I would get these stars, right? These are all the stars. So if we let me make it a lighter color so that it's not too, it doesn't disturb us. And you can see the red stars, the brighter ones. I'll make them instead blue. Let me make this blue so that these ones are our members. So these are all the stars and these are our members. How do we know these are members? Let us again click on form, right? And here what we are going to do is when you click on forms, click on sky vector. Okay. So we are going to basically plot all the velocities of these objects using the sky vector. So I have this sky vector over here. And here, what we are going to do is the length of the sky vector is going to be coming by my proper motion. So here I will write this thing over here as my proper motion in RA. And here I will write as my proper motion in DEC. So here you can see are my stars, their velocities. I'm going to slightly scale this. So here you have a scaling factor, which is given over here. We'll reduce this, right? And you can see very well that all the cluster members, which are these blue stars, they are all moving with the same velocity, right? While the yellow stars, which you can see, these are all the stars in this region, right? They are all the stars in this region, but you can see that all of them have velocities in different directions, right? And that is why they do not belong to the cluster. So 1893 is a set of stars which are born from the same molecular cloud, and hence they are at the same distance, which we found out was about 4 kpc, as well as with the same velocities, which we can see over here clearly in our velocity vectors. We can see that all these stars seem to be moving with the same velocity, right? And that's why these are all cluster members. But you can see these other arrows, right? These are stars which are in the same region of the sky, right? They belong to the same region of the sky, but they do not have the same velocities, and hence they are not members of 1893. So if we are looking for members of 1893, then in that case, these are the members of 1893, right? Now what I can do is I can save this. For example, I can with TopCat, if this is TopCat, I have selected row subset C. So I can save file and I can say save table. I can save this table, right, in the browser, and I can save this table as NGC 1893, right? The VO format is called the VO table format, and that's the best format to save data in because that is the easiest for VO to actually access, right? So we will say VO table data, and I can say, okay. So this gives an extension of VOT, and that comes over here, right? So I have saved this data file on this. Now, there is one way in which I can actually do interoperability, and I can actually send this data to Aladin, right? The other way is what I was showing you is that if I actually have Aladin, I open Aladin over here, right? This is my 1893. I can even overlay the file which I had saved, right? So I can overlay this file. I can say load local file, right? This is the file from this thing, the desktop. And this is my file called NGC 1893 VO table. This is the file. And I can say open. So what has it done? It has opened this file over here, right? So this is the region over here. And here you can see that it is indicating that in this region, these are the stars, which are the stars we identified to be members, right? So the members of this thing are this. I'm going to change this color so that it is easier for you to notice. Otherwise, the picture is a bit too red. So we'll make it the cyan color. And here you can see overlaid on this image are the stars which are members of 1893 marked on this, right? Now I can even visualize this with various other things. I can also see it, for example, with the, what Aladin does is it lets me keep planes. So for example, I have to have one image file. If I take the DSS image, I can put the VO table on the DSS image. If I opt for the WISE image, I can put it on the WISE image. If I opt for the 2-mass image, right, I can overlay this catalog on the 2-mass image, right? So I can actually visualize whatever I am talking about. If I want to see details about a particular star, I just need to mark this region, mark a certain star, and then it's going to actually give me details about that star. So for example, if I want to know this star, you can see it gets highlighted in the table, and I can accordingly. I can also work reversely. If I mark on the table, I can actually find the star I want in the image, right? So it can work both ways. I can actually get the star by marking from here and seeing it in the table, or marking from here and seeing from the table. So here I can visualize all my data using Aladin. On the same side, with TopCat, this data which I had identified, I can further do analysis with this data using this. For example, the simplest thing that I can do with star cluster data is to plot an HR diagram. How do I plot an HR diagram? I click on this, the plane plot. And the HR diagram is what? On the x-axis, I need to put color. So my color over here in Gaia is BP minus RP. So I do this BP minus RP. My y-axis is G magnitude, right? So I will click on, right? I can either take BP mean magnitude, or even there is plain G magnitude. So you have G mean magnitude, and this is my HR diagram. HR diagrams have the y-axis flipped, so I will flip it, and this is how it looks like. And you can see that this is already plotting only for the members. If I were to plot all the stars, right, I would get a mess like this. So the blue stars which you see, or I will change it to a more comfortable color, the orangey stars, or let me make them, okay, we'll do this orange, and I'll make the members as blue like I did earlier. So what you can see is that the yellow stars, these are all the stars of the region. So you can see that this is an HR diagram which has stars all over the place. But if I only choose the selected members, then I can see something like this. And this HR diagram is actually the HR diagram for NGC 1893, right? So what we did in today's exercise is I showed you how you can use TopCat to actually download Gaia data, EDR3 data, for a given cluster. And that given cluster, we can identify the possible members of that cluster, right? By making cuts. First of all, we plot it versus proper motion RA, proper motion DEC. Then we do a histogram with distances, because we know that all these stars have to be at the same distance. And using that, we can identify the members. If we want to visualize these members, we can visualize these using Aladin, right? So using Aladin, we already have our image. Like I hope I mentioned, Aladin has all these planes. So I can always remove a plane, or I can add a plane, right? For example, now I can add the WISE plane. I remove the 2-mass plane, right? I can add the WISE plane, and I can add, here are my Gaia stars, and I can add this. I can add various other catalogs also to this, right? We don't have the time today, but if you actually see over here, you can actually choose in catalogs. You can click on catalogs, and I don't want all the catalogs. It thinks I want all. And you can actually search for catalogs for whatever you want. So this is actually telling you that the number of catalogs it has for this region is 25,996 catalogs, right? So there's a very large amount of catalogs available for this, which could be loaded. Or you could search for the catalog using some other search things. Whatever you want, you can search for it over here and look amongst various catalogs and missions. So what one can do, we don't have the time today, but you can overlay over here various, various catalogs plot these stars and actually look at the stars as they seem to you in this image, right? And this can get correlated immediately with what's over there. I'll just show you all for a minute. I could not show you all the ADS thing. So I'll just show you the ADS thing because now it should be fine. So let's do ADS. So if I say ADS NASA also, we'll get that. And this is what I was showing you right in the beginning. You can actually access, supposing you've already got the members and you would like to know what is the work that people have done with this, right? You can actually use this search engine to actually get the thing. So for example, in abstract and title, I can say for abstract and title, I can write over here 1893. I can search. And like we saw earlier, you can see that this is giving you all the results, 1,810 papers written on this thing, all of them which you can see over here. And if you, for example, let us go into, you have, or not all of them are for this cluster. You can see that, for example, there is this paper. So you can click on this. And over here, you can see this is the archive paper. This is the publisher. There's no data over here. So I will try to look for a paper which actually has data. And this is a bit too new. Let's look at something slightly older. So I think I should improve this and make it NGC 1893 so that we get more. Yeah. So now over here, we are going to look at specifically this cluster. I can click on this, for example, right? And here you can see is that supposing this paper, they've studied variable stars in this NGC 1893. And you can have the whole paper available over here in the publisher version or the archive version. And there are certain data products. So you can actually log in over here and you can get the data products, download the data, right? It also gives you lots of other detail about the paper. In the sense, what are the references and what are the other data sets about this, right? So we can go into that and you can see that. So we go back to results and so in short, ADS will also give you a good way. For example, over here, you can see NGC, this thing with the X-ray properties, and you can actually see, this is, you see that for this paper, for example, it's showing you what are the citations for this paper, which are mentioned over here, right? As well as it's showing you the references in this paper. So you can get the references in this paper. You can see the co-reads, which are similar papers. ADS actually lets you have an account. You can make an account, you can log in, sign up for it. You can have a login. If you log in, you can actually enter your email address, make a password and do that. And you can actually have a library of your own of your references sitting in ADS, right? So this is the ADS thing. So I will actually stop now because I would like to take questions from the others. I hope you, with this, what I was basically trying to show you of how could you get comfortable with using ADS, TopCat, Vizier. Similarly, SAO image also, if you have an image, you can view it in SAO image or in Aladin, whichever one you want. And in that way, you can combine all the data you are getting in various wavelengths in a very seamless manner, right? In a very easy manner, so that you can easily, use all the data that people have got till now on a certain object and get a complete consensus of what is there on this object. Like I said, here when you're seeing the papers, you'll immediately know what is the kind of work that has been done on this cluster and how could you actually, improve on it or add on to that work with your own unique research, whatever you're planning to do. So I will stop over here. We have 6 minutes more, and I'd be happy to take some questions. So I'll give this time a little bit for questions, and I'll stop sharing the screen. I'll put on my camera, and please let me know if you have any questions. Yeah. Yeah, Eugene. Yeah.
Yeah. I have a question.
Yeah, please.
When you save the subsample in TopCat, you
Yes.
save as a VOT file.
Yes. Yeah.
Can you save the files in any other type of files, ASCII files,
Yeah.
.dat or something like
Yeah,
that?
you can. You can, for example, save it as an ASCII file or a CSV file. You can do that. But what happens is that since VO table format is the exclusive one made for VO, so if you want to use the same file, for example, in Aladin or in different, VO services, we did not get time to talk about VO plot, VO stat. There are many more VO services. So often it is safest to put it in VO table format so that nobody has a problem with the format. But in principle, CSV is the next best option. The comma separated variable, that's also good. That would be good. ASCII is not very good because supposing you have missing values, then it becomes difficult for it to, realize where is there missing values. Because often in the data, there can be missing values. Specifically Gaia data, for example, radial velocities are not there for most sources. Maybe parallax is also not there. Yeah, so that's it. Yeah.
Yeah, and I have another related question, but I think that you answered already. That when you upload the file at Aladin, the format has to be VOT, only VOT to upload the file.
No, I think it will also take CSV. It also takes CSV. CSV it takes. But ASCII is not a good format because ASCII, like I said, missing values. It has a problem in knowing where
with
the
blanks,
yeah,
or
yeah,
something.
that's right.
Okay.
So CSV, what happens is even if there's a blank, there'll be commas before and after. So it will know that it's a blank. But with ASCII, it gets confused. So CSV is fine. You can do CSV. So that CSV, you can do it even if you're working on Excel. If you work on Excel, then you can save it in CSV and that's fine. That will work. Yeah.
Thank you.
Welcome. Any other questions or?
No.
Yeah. Okay.
Priya, how do you say your names? I'm sorry, Priya.
Priya. It's just Priya.
Okay.
Priya.
We have another half an hour today. It was longer, your session. If you want to use it to continue telling us another stuff that if you want, because it is very interesting, and we have half an hour more to.
Okay. I thought it's only 1 hour today. So
No,
I was, stopping with 1 hour.
But we can finish here also. I don't know people who is attending.
The others are there because the others are quiet. I don't know.
Yeah.
Okay. So I'm not very sure whether.
Okay.
Because if this was with Gaia, but now if I say supposing do it with SDSS or HST, then that would again take another, it'll take some time.
Yes. Well,
yeah.
It was very good so far. So
yeah, thanks a lot. Thank you.
We can finish here.
Yeah, then I think we'll finish here because the others are very quiet.
Yes, are quiet.
I'd be happy to do it, but I think the others are.
Okay. Okay, I will stop the recording now.
Yeah. Okay, thanks.